Hello everyone, my name is Jose Pena. I'm presenting my final project, which is the metal subgenre classification. Okay, so the goal is to classify metal songs into 10, in this case, 10 generic subgenres of metal. And I'm going to be using Spotify endpoints to prepare a data set, and then Keras machine learning API to build and to train CNN. Classifying songs, um, metal songs into one of its subgenres, it's quite difficult. Um, Initially, I used a 25 subgenre list and the corresponding songs, and finally merging everything, we had a 10 subgenre list that had nearly 5,000 songs. We know that CNN models perform really well for image classification, and that's why we try to leverage this um, characteristic, and we tried to transform the picture of songs into images, and we sent this to a CNN model. We found we had a very imbalanced data set, and this is very important. And we tried to overcome this implementing data augmentation strategy that consisted of creating artificial or synthetic songs from original songs. I used the regular software Anaconda, Python 368, Jupyter Notebook, and also the regular Python packages, TensorFlow, Keras, and Pandas, NumPy, Spotify, a lot of supporting libraries. Also, I use TensorBoard, Spotify endpoints, and GitHub to upload the final dataset. I used Windows 10 and a GPU for this project. So I needed a dataset that had metal songs labeled into some of their subgenres, but there were not any data sets with this information, not even a million song data set. So I had to create a data set from scratch. I started from this page where there was 25 list, a 25 journalist with one playlist per subgenre, and from that I downloaded all the songs and merged all the songs, and yeah, I'll show you what I did. Anyway, so songs can be split into time segments, and each time segment has interesting features. It has the pitches, which is a 12 chroma vector that corresponds to the 12 pitch classes, all these classes that we have here, and also the timbre, which is another 12 element vector that corresponds to the 12 first principal components that were computed over the spectrum of this patch of the segment. The final dataset contains these features. The final dataset is quite huge, so I uploaded to GitHub. I have to change this URL actually. All right, so this is the project steps. I'm not going to over it because it's almost 5 minutes. All right, so the starting point, as I said, it was the 25 Spotify playlist and the subgenre. So we process everything until we have this other data set with the artist, subgenre, track ID, and the track name. So So after merging all the subgenres, we finally came up with a 10 list, with a 10 subgenre list. This is the final list. As you can see, it's very unbalanced. This was a problem, but we'll go over it later. Then what was next? So we use this endpoint from Spotify, the audio analysis for a track. What does it mean? This means that every track has Spotify for every track has an endpoint to get a variable number of segments of variable duration, and each segment has this pitches information and this timbre information, as you can see here. This is the pitches, this is the timbre, this is the 12 element vector, this is the another 12 element vector, when it starts, when it ends, and this is the main features that I used for the problem. Then the challenge was to build a 12 by 1800 matrix, and that's what we did. What I did, establish a regular interval of 0.1 seconds sampling, and establishing this sampling interval. Then actually we cut the song in 180 seconds, so that we have 1800 samples with 12 features. So that comes up with this 12 by 1800 matrix. As we have two main vectors, we will come up with kind of a two-channel tensor. That is quite similar of what we did for image classification. So it's similar to the RGB that we did for image classification. And we saved the tensor of each song into NDI file. And so we have this in the disk. So that's the code that we used for this transformation from the vector to the tensor, the vector for the tensor. Okay. All right, so this is the result. So this is the 10. This is a representative for each subgenre. Here we have alternative, new, groove, or rap and funk. Here we have folk, German, hard rock, or glam. So, and this is the timbre. Sorry, this is the pitches. This is the timbre. As we can see, there are differences. So we don't know what this means, but there are differences between different songs. So there might be good information here. So before fitting the images to the CNN, we have to split this into a good partition and set it to disk. So we created a 70-20-10 partition, 70 for training, 20 for validation, 10 for testing. So this is the split of songs that we have. You can see it's still unbalanced. We are getting close to it. So we have this number of trained images, this number of validation images, and this number of test images or MPY files. Remember, an MPI file, if we display this is kind of an image. All right, so then we had to implement something to augment this to try to balance the songs. So we went from this point to this point, and how we did it. So we made up something. So the principle that we use is, okay, if a music expert is able to recognize a subgenre by listening the subgenre of a song by listening to the song just a few seconds, why couldn't we do that So what we did was we split the 1,800 samples in chunks, for example, in 3 chunks of 600 samples. And then we shuffled these 3 chunks, and then we came up with a new song. We did that for the classes that had less, as you can see, less number of songs to try to balance everything. Okay, that's what we did. This is the process. So this is the song. We split that in 3 parts. We shuffled, and this is the new song. I don't know. That kind of worked. So the overview of the data set is this is the average of each pitch or each timbre along of the sounds of each subgenre. So we can see that there is differences. So this is good news, because that means that there's signal here to recognize. Okay. All right. So we are getting closer to the CI model. So we are using, this is one of the examples that we used. I've used a lot of different architectures to try to come up with the best one. I haven't found the best one yet. I'm a day away from the deadline, and I still haven't found the best one, I think. But okay, anyway, it's 3 CNN plus max pool layers, and then 2 dense plus the final layer. This is the TensorBoard graph. All right, so the CNN model. So as I did a lot of changes, a lot of combinations. Finally, I needed to build something that was easy to work on. So there was a section with 1 to n layers of convolutional plus max pool, sorry. Then a second section of dense layers, then the final dense layer of the 10 units with a submax activation, and the optimizer that can be stochastic gradient descent or Adam. So this is the basic. So it's 2 very customized portions or sections, and then another 2 parts that are easier. Okay, so these are all the parameters that we can use. So for the convolution plus max pooling, we can personalize all these parameters. So the number of layers, and the filters, the kernel size, the stride, the regularizer, if they are regularizer or not, the kind of regularizer, the value, the lambda value, the dropout, batch normalization, the batch pool, the size, the stride, the type of activation, and the type of initializer. So we can change this very easily. For the dense, pretty much the same. The number of dense layers, units, dropout, the dropout rate, initializer activation, and then the final dense layer. There is a lot of parameters. And we can change this easily. This is the main function. As you can see, this is all the parameters. But once you have all these parameters, everything works automatically. So you can build 1 to n come to the plus max pool. Here you can build 1 to n dense layers, and this is the final part, which is the final dense and the optimizer. So with this part, which is just the parameters, if you fill out this, you can try a completely new architecture, and that's what I tried. Completely new architecture easily. So observation. So to me, shallow models work better than deep models for this data set. So with 2 columns, 2 dense worked better than 3 plus columns and 3 plus dense. So with enough capacity, the model processes well, but yeah, it suffers to generalize. So validation accuracy doesn't get beyond 50%. Anyway, this is good because it's 5 times more than random chance, but going over 50% is quite difficult. And the validation loss normally flats after 20 epochs. So the overfit, I tried regularizer, dropout, augmentation, and even so, it's very difficult not to overfit. Very difficult. The model training. So this is kind of a summary, as you can see. So it trains very well, but it plateaus after 20 epochs for the validation accuracy. So this is interesting because this is a chart that says for the correct classification, what is the distribution, which ones were best and which ones were worse in terms of percentage. And in totals, for example, here we have hard rock. It's the best one in terms of classification. Or symphonic, Gothic symphonic is worse. So this is interesting. So lesson learned. The quality of classification. So this is obvious, but the starting point was the 25 playlist. It was very personal, biased. So I don't know if it's the best starting point. I don't know. This overlap. I don't know. The quality of classification. It's really important for the outcome. Balanced and unbalanced classes. The data set, it needs to be balanced, obviously. I got better results when I balanced, but it took me time to balance the data set. Overfitting, it's by far the most important problem, more critical, and I'm still dealing with him. And the architecture is an art, truly is an art. So many combinations, sometimes you don't know what is working and why it's working. So now I understood really what this meant. I read this a lot of times and now I understood. And to save parameters, so it's very important to have a way to save parameters, save models, because you do so many combinations that you start to lose track. All right, so this is it. Thank you so much. I hope you like it. Thank you.